Hello and welcome to another Thinking Particles tutorial video. While browsing the internet, I came across a really cool visual effects video. I thought, hey, we can do this in 3ds Max as well. At least this is what I thought. In parts, it turned out to be true. We can do these effects faster and much easier, also better with much more control. However, as it happens so often in visual effects world, looks can be deceiving, and things that seem simple turn out to be really evil and complex. Let me show you what I mean. I'm your host, Edwin Braun, and I'm thankful that you're watching this video. Please leave a like and subscribe, and I will keep on creating more free stuff for you. Let me bring up the animation first I saw, and then we can discuss how we can create this animation. Let's bring up my inspiration. Here we go. So this is the inspiration from NVIDIA Studio. They have some tutorial videos, and I saw this one. Let me just play back the introduction. So that's creating a fluffy 3D Rubik's Cube, and I found that it looks really, really cool and amazing. Let me just move forward to when he starts with the cube stuff. There we can see again what we wanted to achieve. So these are all these fluffy, squishy, air-filled cubes, and that's practically the animation we are after. So that was my inspiration, and I thought, hey, I can do that as well in Thinking Particles, because Thinking Particles is procedural. So he's doing that in Houdini, obviously, and he's using immense complex. It's a 4-part or 5-part training tutorial, I think, with a lot of in-depth Houdini craziness going on. That's the first warning I want to give you. So even though it's a Rubik's Cube, it looks really simple cubes and stuff, but it's more complicated than that. I found that out when I tried to reproduce these effects, because we now have to deal with kind of things like rigid bodies, soft bodies, the cloth simulation. Then we have to rotate this cube somehow, and I wanted to keep it fully procedural. So that means I wanted to change the amount of cubes and everything. So everything should be fully procedural. I will show you how I created this effect. I will just show you the result and go through what I did and how this setup works. I will go into every little note I used and why I used that and how it works. So let me just first bring up my first step I did. Obviously, my first step was not using cloth or soft bodies. My first step was just trying to get the Rubik's Cube turning and working with physics, rigid body physics. So that was my first idea. Let me bring up Thinking Particles. And here we go. So in the Create Dynamic Set, or better, let me start, rewind, and let me explain what you're seeing here. Probably, or perhaps you are not so deep into Thinking Particles or have never seen it before. In Thinking Particles, we have these particle groups, so where we can have any amount of hierarchical particle groups. So this is just a little container where we put particles in. And down here we have our simulation nodes or dynamic sets, what we call them. And my first dynamic set is called Create. So this is where I create the objects, and I also in the Create group, I'll do the simulation as well. So probably I should rename that in Create and Simulate, to be more accurate. So now we renamed the group in Create and Simulate. So I create the cubes, and I'll also animate them in there. Then we have a gravity group, dynamic set. In the gravity dynamic set, I just grab the soft body particles, which are right now our rigid bodies, but doesn't matter. The name of the group is soft bodies. And then I'll just apply a standard force that pushes down everything in the scene with physics. And then we have our physics solver dynamic set. And there we use our bullet physics solver for the cloth and rigid bodies as well. And we have a floor node so that objects can bounce around. Let me just replay that again. And this runs here in real time. So the animation you see is in real time, the simulation in real time. And keep in mind, we have 4K recording on the same old crappy machine I'm using here for my 3D Studio Max animation and simulation. That is the basic amount of dynamic sets we use here. And when you compare it to things like Houdini, it ends in endless nodes and craziness with coding and stuff. We will have to do some coding as well, and I'll explain why I chose that route, and we'll see. Let me just go here. So now we have the option, how do we create a Rubik's Cube? So what we wanted to have is the classic Rubik's Cube. And as I mentioned, I said I want to have it procedural. So I wanted to have a 2x2 cube, or a 3x3, or 4x4, or 5x5, and so on. We have to keep in mind, if we overdo it, we need to supply more particles. So let me just do that a little bit more. And you can see by that, just adjusting some parameters, we can create all kinds in a procedural way. So 4x4, so we have 1, 2, 3, 4, 1, 2, 3, 4. So we have a 4x4x4 grid, 3x3x3, that's the classic Rubik's Cube. And we can also go crazy and higher or lower. So that is what I meant by I wanted to have it procedural. And the good idea is to have it procedural is depending on your machine that is doing the simulation, you can start setting up with only a 2x2 grid. So that gives you an advantage when setting up the effect, the visual effect. Because when you're done, you just dial up the amount of cubes you want to have, and you're done. Let the machine calculate and simulate, and all is fine and done. Next thing we want to do is the cubes created. So how did I create the cubes? I'll use a little MEL script. MEL is our scripting programming language inside of Thinking Particles. It's a very powerful, fully multi-threaded scripting language or programming language for Thinking Particles. And it's so powerful, what you can do with one line of code might need several nodes in if you would do it in the classic way. However, let me just show you. This script here creates our cube. So it's just that. Most of it is declarations of user interface. So that's UI. I want to have an input for our group, an input for our raster, cubes amount. So I want just these user interface parameters here. We have our born, pistol shot, we create particles we can use. Let me just dial that back to 27 because we want to only create 3x3 at max. We have our geometry instancer where we instance the geometry, so cube on each position of the particle. So most of it is just declaration of what we want to have, variables and the user interface options. So that's our adjustable inputs here. And the rest is just this little for loop where we just create particles, or we are not creating the particles in there. Our particle born is doing that, but we grab the particles. They're all at position at the origin. We are all placing the particles with a set particle position here. So what we are doing is we go through the particles in a raster. So we specify the raster with an input, the raster input. We declared we want to have a raster input, which is a scalar value in world space, and that's it. So we specify the variables and go through. And now the interesting part here is there is no for loop or anything. So how do we get all the particles and place them in the right grid? That is where the parallel or multi-threading comes into play. MEL is a multi-threading or multi-processing scripting language. That means when you have as a first input a particle group input, which we have here, our particle generator, that means we're going through all the particles in parallel. So if we had 1,000,000 particles, we would work on them in parallel. So as many threads as we have, if we had 64 threads, 64 particles would be evaluated at the same time. Right now, we get all the particles divided by all the threads, and we got them passed into our script. So all we need to do is this little magic ID thing. So that tells us, hey, here's the first particle, here's the second, here's the third, here's the fifth particle, and so on. So we use that, so to say, as our for loop until we get all the particles in, we place them in the grid, and that's it. So this is how we calculate the positions, place them there, and I'll scale the instance a little bit smaller so that we have a little bit of a gap between the cubes so that they can extend later on. And that's practically it. There's one more trick we're doing here. We are creating in parallel ghost particles or joint particles, however you want to call them, ghost or joint particles. So I create another set of 27 particles here when we had the 3x3. Now we have the 2x2x2 particles. So I create another set of 8 particles that are my ghost particles, and those particles I will use to correct for any shift or drift I might have through calculations. So that's the first part. As I mentioned, very short script. That's all placing the particles. It grabs the particles, positions them in the raster. Very simple. The next thing we do is the drift compensation. I will talk about why we need that, and the animation of the cube. However, let me just show you as an example. We have this one node to create the particles. How would you create the particles in a standard thinking particles way? So that would be the setup you would usually use in with thinking particles nodes. So you would say, okay, I want the amount of cubes, a 3x3 grid. Let me just show you how this works. Let me turn off this one. Let me turn off the physics as well. So we are now concentrating. I'm only activating this make cube. Now we are creating the cubes here with our old method. Let me just move that here and make sure we have a reset of the simulation. So what we are now doing is we have the same amount. I can adjust the amount of cubes as well, as you can see. So we have the same deal as I have with the MEL script, and we are using an iterator. Our first iterator is responsible for the X, and we put in the amount, the count. In this case, it's 2. And then we have an iterator in Y and Z. So we have all the X's, and in our point, we specify the value we want to multiply. So our first particle is 0, so that would be position 0. Second particle is 1, position 20 millimeter in X, and 2 would be 40. So we can add up as many cubes as we want. So now we got the positions X, Y, Z, and we specify that as a point in here. And we also specify how big the size of our particles. Then we generate the particles here. We born them per call, 1 particle. And we do a geometry instance as well and assign the cubes to our particle. So that would be the normal way, or the old way of doing it. Let me just turn that off. I went with that because it's much faster, more controllable, and really easier to do. We created here our particle grid along with ghost particles. So keep in mind, we have now double the amount of particles. One stays in place, the other one can move or do whatever they want. So now let me show you how we animate the cube. And now let's have a look for our drift compensation. So why would I need something like a drift compensation? I added this because I wanted to make sure that with the cloth simulation, and the bullet cloth is independent of our particle position. So the cloth is moving around the particle. We have these particle-based bullet simulations. So it's kind of tricky. So I want to make sure that we are not getting a drift through the cloth itself, and also we are not getting a drift through our calculations because we add a rotation value all around, a little here, a little there, a little here, a little there. And the more you do the rotations, the more inaccuracy you might get in your equations. So this is why we are using the drift compensation. And for that, what I do is, whenever we have a full rotation, so we have a full rotation in 1 second, and that means whenever we have a full rotation, then this code is called. And all I do there is I just go in here and say, okay, I want to position the particles back to their original position. So this is all what I do here. I'll recreate the particle positions again. So I'll move them, whatever inaccuracy, I move them to the original initial position back. And here in this script, our animation, that's the interesting part, that is responsible for the animation of our cube. The rotation we have, as I mentioned, 1 second per turn, and we are picking random layers and random rows, or random columns and random rows. So what we have here is we are going and pick a random axis, and we want to pick a random axis by just using obviously a random function, and then we will rotate around each of the axes we pick. So the axis we pick actually in our drift compensation, where we assign the random axis. So if it was not assigned, we just say, okay, give me here a random value between 0 and 2. So that would mean any of our axes, x, y, z. So that's our rotation where we want to rotate, and pick any layer or row that would be between 0, 1, 2, or any other row we have there. And that's practically all. So that all our scripts can access these planes and axes we pick, we store them in a memory. So now this script can access what I picked. So did I pick this first row in this axis, or did I pick this layer in this axis? And we get this random 0 to 1, 0 to 1, and then we just go through a simple if then else situation where we say, okay, if the axis is 0, we pick the x-axis. If the axis is 1, that means the y-axis, and if the axis is the c-axis, we say, okay, let's take the c-axis. Then we rotate the object around, and we do our position correction as well, and we do a little bit of a velocity compensation as well. So now that we have that, so we animate our particles around the axis, we created them. So all that is left to do is we access all our particles again we created up here in our softbodies particle group. And then what we are going to do is we are just assigning either a rigid body or a soft body effect. And after a certain interval, we assign at frame 201, we assign a little bit of a random velocity in all directions to kind of explode our cube a little bit. And we turn off all our animation and drift compensation so that we actually can explode our cube at frame 200. So after frame 200, this is turned off and we have no more animation and compensation happening. And then we can see after we rotate, every rotation is taking a second. So regardless how many subframes or whatever we have, it's always a second it will take. And then we have our rigid bodies going here. So how about if we just swap out our rigid bodies with soft bodies? Do we get the effect? The important part to note about rigid bodies is I'm using a pressure-based model. Bullet offers us a lot of different cloth models, and one model is a pressure-based model. So that means it actually has a certain pressure inside, and it can blow up objects or inflate, deflate objects, and all this kind of effects we can do and probably simulate. We can even add on top a volume conservation. That means it tries to keep the volume. So if you push in one side, it goes out the other side, or all the other sides. So you can add that on top. So I set up this pressure-based model. When it starts with your original geometry. So it needs some time to blow it up to the target pressure we set here. So we can set this pressure now, or I've set the pressure now. So in the first 20 frames, nothing happens. So we will have a phase, and then I will start rotating. We have an animation delay. I feed that into my drift and animation cube. The animation delay is in frames, 20 frames. Let's have a look in our script where we get the animation delay. And as you can see, we get the animation delay in here, and we start our simulation only when we don't start it at frame 0. We just don't want to have it already rotated. And we don't want to start before the frame of animation delay is reached. So that's all we put in here, and we do that in both scripts. And that's why for 20 frames, we take the time to blow up our cloth and kind of get it stable, and then we can start rotating. Keep in mind, right now I have a very low setting of subframe steps. Later for final rendering, you would just dial up the subframe steps and that's it. But we can see it's still pretty amazing that on my old crappy machine, including 4K recording, including audio recording, all the stuff that's going on right now on my machine, it still simulates in real time here our soft body cloth collisions with each other. We even have self-collision inside of each fluffy box cube. And then we have the explosion, cubes falling down and bouncing on the floor, compressing, bouncing off each other. So we have all kinds of amazing, nice effects we have here. So that's the setup we have. And then I thought, that this tutorial I saw there for Houdini, they reassembled the cube, destroyed, reassembled it again, and so on. I said, okay, that's good, but let me do something else, because with our bullet implementation, we have something called Hero Cut. And that allows you, the Hero Cut allows you to actually decide how a cloth tears and where it tears apart. You can tear it apart with a map. You can do all kinds of amazing things. And I'm using just a cellular map here to tear the cloth apart. And we want to deflate the cube. When they tear apart, air gets out, poof, and we just have the hollow shell here. Let me just show you what I mean and how I created this little setup here. So that's now the fully rendered animation. We have the 3x3 cube and the cubes fall down. Now we increase the pressure. It's just an animation of the pressure. Then we get tears. It deflates and flop. We have just the bare cloth on the floor. I found that animation pretty amazing, and that's just one way we could control every cube individually, all kinds of stuff. It's fully procedural. We have all the freedom. We can control and do whatever we want with our animation right now. So I think this is really turned out really good and amazing. And as I mentioned, we used here all the procedural approaches we have in Thinking Particles. Let me just load the pressure scene where I have the setup for the pressure, which is higher subsample setup, but let me just bring that in and load in the scene. Okay, here I loaded the original scene I used in the animation. Let me just zoom in a little bit here so that we see what's going on. Just a short reminder, here's the video playback again. We have our fluffy cubes with collision detection between the cloth, falling down, blowing up the pressure or increasing the pressure until they deflate. And that's it. That's the scene, and let's have a look how I added the effect of the animated explosion or blowing up. Here I have the blow up, the plop. I named that dynamic set plop. And here is our initial setup we have here with the soft bodies. So what I did here is I control one specific parameter, the global friction. For the animation of the twisting and rotating the cubes, I have a global friction to get the wobbly stuff under control of 0.1. But when it falls down, I don't want that. I want the floppy things. So when it falls down, I just dial that down to 0. So that's the only addition I did here. And now for the plop. So the plop kicks in at frame 350. This is when I activate, so they fall down. This is when I activate my soft body plopping. So what I do here is I use a value to value. I increase the pressure to 8,000. That's my value here. I put 8,000 out. 8,000 multiplied by 1 for the maximum. 8,000, and then poof, air is out and it drops down. We could have a slow drop down as well. Whatever we want, we can control how fast we blow the cubes up. Then I'm going to do here a little bit of crazy control of bullet and a little bit of magic. So what I'm doing here is I'm controlling the pull and push stiffness, because when the air is out, I don't want to have it behave like its original cloth. So bullet cloth is a spring-based system, so it would try to create the cube, even if it's just in torn pieces, it would try to recreate the cube. So this is why I set this to 0, pull and push stiffness. But I have to be aware that in all other cases, it should not be 0 or it will just deflate. I turn that to 0, and the same for these two values, the dampening. I don't want any dampening anymore, and I don't want any global friction anymore. So I turn that down so that we get just the fluffy hull cloth on the floor. And then I want to make sure I have no more volume conservation. I want to make sure that our breaking is happening so that we can tear the cloth apart. And one more thing, our hero cut, that's when the actual tearing and breaking happens, is happening as well at the same time. So I'll activate the hero cut and it tears apart our cloth automatically. We could do, let me just go here. Okay, that's it. That wraps it up. Thank you for watching this video. I hope you enjoyed it. We will make these scene files available in our next release of Thinking Particles. If you have any questions, just leave a note or comment. We'll answer it, or send us an email. We are happy to help you out and hope you enjoyed this video. Goodbye.